In this section, we'll talk about a technique for identifying maximum and minimum points along an interval. Let's take a look at this graph. In terms of max and minimum, this is a relative maximum point. Now, I say relative maximum because there are points that are higher than this on the graph if we go all the way over here. You see, this graph actually seems to go up without bound, and so there is no absolute maximum point. But this is a maximum point within a particular neighborhood, within an interval, you see, around this hump sort of in the graph. And that's what we're after. We're after this relative maximum point and the relative minimum that is in this area of the graph. Now, these values are generally referred to as extrema. You see, extrema. Extreme values in relatively small intervals of our graph. So we're looking for relative maximum and relative minimum points. And it turns out that derivative helps us in this process because the relative maximum and minimum points must occur at the critical numbers of the function. Now, critical numbers of the function, this is almost a little misleading here. Remember that critical numbers we found in the last segment are values that are the zeros or the undefined values associated with the derivative function. And those are the critical numbers. Those are the ones that are referred to here. That these relative maximum and minimum points must occur at the critical numbers of the function, but they are found by using the derivative function. And we apply them to the function in order to find these maximum and minimum points. An example would be in order here in just a second, but let's talk about the first derivative test because this is the way that we're going to identify maximum and minimum points within an interval. If f prime of c changes from positive to negative at c, then c is a relative maximum point. Now let's talk about that in the context of a graph. Let's come back over here. You see, f prime of c, the slope of the tangent line, you see, we can think of it that way, changes from positive, you see, to negative. When it changes from positive to negative at this point c, then that point c must be a maximum point, a relative maximum point. And on the other hand, if the derivative function changes from negative, slope of the tangent line negative, to positive at a point c, then that point c must be a relative minimum. That's what the first derivative test is all about, and here's how we use it. Take a function like this, and notice that we're not really looking at the graph. If we have the graph right in front of us, then sure, we can kind of look at the graph and say, oh, there's a relative maximum and there's a relative minimum, and maybe we can use the trace feature on the calculator to identify the exact position for relative maximum and minimum points. But we can perform those operations algebraically, and the algebraic method is necessary when those points happen to be, let's say, irrational. You see, they might be easy to identify if they're rational values, but if they're irrational and we want the exact position, then we need an algebraic method, and this is that method. We start with the function and we take its derivative, and the derivative here is 4x cubed minus 6x squared. All right, now we'd like to identify the zeros or undefined values associated with this. There are no undefined values, so we factor here, and now we want the zeros of each factor for our critical values. Well, the value of x that causes this factor to be 0 is 0 itself. The value of x that causes this factor to be 0 is 3 over 2. So those then become our critical numbers. Now, these critical numbers we are going to apply to our function for identifying relative maximum and minimum points. But we use the critical numbers in much the same way that we did before in talking about increasing and decreasing ideas. We subdivide the number line into intervals, and the intervals are from negative infinity to our first critical value, and from the first critical value to the second one, and from the second critical value to infinity. And then we make decisions like this. We decide whether or not the derivative is positive or negative. Now, again, we could see this if we were looking at the graph, we could see whether or not the function is decreasing or increasing along these intervals if we were just observing the graph. But we can tell algebraically by choosing a value in the interval and putting it into our derivative function. And if we take big negative numbers, which are in this interval, and apply to either of these two forms of our derivative function, we'll see that the function is negative. And let's verify that idea. Big negative number squared, that's positive, so this factor is positive. Big negative number times 2 minus 3, negative. Negative times positive, negative. So the derivative function is negative for big negative values, so in this interval, the derivative function is negative, and therefore the function itself is decreasing. So the graph is decreasing along this interval. Now let's go to the next interval. Now the tendency is to think that we have an alternating situation, that if in one interval we're decreasing, then in the next interval we're increasing, and therefore, let's see, if we're decreasing and then increasing, we have a relative minimum at that sort of juncture between the two intervals. Well, that's not always the case, and it's not the case here, because look at what happens. In the interval from 0 to 3 over 2, and we can take a test point like, let's say 1, within this interval and apply it to, or plug it into, our derivative function. So putting a 1 in here, this becomes 2. 2 times 1, 2. This is negative. Negative times positive is negative. Wow! The derivative function is negative for values within this interval, and therefore the function is also decreasing along this interval. I don't want to say continually decreasing because it goes flat, you see, at this point 0. But it's decreasing again along this interval. And what we know about that at this point is that the graph is sort of, and let's slide over here and take a look. The graph is sort of doing this. It's decreasing, and then it goes flat, and then it decreases yet again, you see. And this then, that point where it goes flat is the 0 point that we're talking about here. All right, anyway, we look into the next interval then, from 3 over 2 to infinity. Well, big positive numbers. Great big positive numbers. Let's see what happens. Big positive numbers squared. This factor becomes positive. Big positive numbers times 2 minus 3. This is positive. Positive times positive, positive. So the derivative function is positive in the interval, so f is increasing. Now, we're going from a decreasing situation on the graph to an increasing. Decreasing to increasing. We have a relative minimum then at this point 3 over 2. So that's how we make decisions like this. Here's another one. This one is a little trickier because of the notion of a fractional exponent. And we go through the process like this. We take the derivative, and here's the derivative of our function f. Now let's manipulate it a little bit into a condition where we can, we're a little bit better able to evaluate the zeros, and we can do that like this. We change x to the negative 1/3 into, now the negative exponent says misplaced base, so this x kicks down into the denominator, and the fractional exponent implies a radical, so it's the cube root of x then that appears in this denominator. All right, now for the zeros or undefined terms. Now, the undefined values we can identify in this condition. What values are undefined here? Which ones are unacceptable? Well, it's not acceptable for us to have 0 in a denominator, and that would occur if x itself were 0. So x equals 0 causes the fraction to be undefined, and therefore the entire expression. And so, x equals 0 is one of the critical values. Let's see if there are any others. We want the zeros for the expression, so we set the expression equal to 0 and solve for x. Now to do that, well, let's see, we'll multiply through. Now there are several techniques that are possible here, but what I did in this situation is to multiply through by the cube root of x. Multiply this by the cube root of x, we get this. Here we get a cancellation, leaving the negative 2. Now adding 2 on both sides, we get this. Divide by 2 on both sides, we get this. Cube on both sides, and we find x to be 1. Well, x equals 1 then is another critical value. So we go over to the side and we identify the critical numbers, x equals 1 and x equals 0. And then we subdivide our number line into intervals from zero to the, from negative infinity to the smallest of the critical numbers. That's from negative infinity to 0. Then between these two, 0 to 1. And then from the 1 to infinity. And then we start to discuss the idea of whether or not the derivative function is positive or negative within those intervals. And we do that here. And that's where we pick up this problem. Now let's see. Big negative numbers is what we're talking about here. And to identify positiveness or negativeness in the derivative function, we plug in a value, a specific value, or we generally just think about the situation. Now, I think this one is relatively easy to deal with, but if we're talking about negative numbers, cube root of a negative number is negative. So we have 2 over a negative number, but this is negative. So we have a positive value here, you see. So a positive number with 2, positive. All right, so f prime is positive then for values in this interval. And if f prime is positive, slope of the tangent line is positive, that means that f is increasing. All right, let's take the next interval from 0 to 1. Wow. 0 to 1. I could choose a specific value here, but let's see if we can just analyze it by looking over at the expression. The cube root of a positive number, now that positive number from 0 to 1, you see, it gives us a positive denominator here, 2 over a positive denominator, and that denominator, we're taking the cube root of a number between 0 and 1. That's a pretty small number, and 2 divided by that tiny small number, gee, this number smaller than 1 will go into 2 more than 2 times. You see what I'm talking about here? Like if it's 0.5, if it's the cube root of some number, let's say, gives 0.5. 0.5 goes into 2 4 times. So this would be 2 minus 4. You see, and a negative value would emerge here for numbers x that are between 0 and 1. So a negative value emerges, f prime is negative, and therefore the function itself is decreasing. That means then, since we're going from an increasing situation to a decreasing situation, now think about that, increasing to decreasing. You see, oh, that's relative max. So we have a relative max at x equals, and we're talking about the point where we change from this interval to that interval. That's the point 0. At x equals 0. All right, let's examine the next interval from 1 to infinity. That's big positive numbers. Let's come back over here and think about that. So we have the cube root of big positive numbers. That's a big positive number. 2 over a big positive number. That's a fraction. You see, that's a relatively small number. And as x gets bigger, 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 this fraction gets smaller, smaller, smaller. So 2 minus a very small value would still be positive. So f prime is positive for x values in the interval. So f prime is positive, and therefore f is increasing. Now we're going from a decreasing situation to an increasing, decreasing to increasing. Oh, this gives us a relative minimum. At, let's see, these are joined at 1, so we have a relative minimum at x equals 1. In our problems up to this point, we have talked about maximum and minimum points in a neighborhood, and we call them relative maximums, relative minimums. And we can't talk about absolute max and min up to this point because our functions or our graphs have gone up without bound or down without bound, and therefore we can't identify an absolute maximum or minimum in those circumstances. But if we close the interval, then we can identify absolute maximum and minimum points. related to that idea is the extreme value theorem, and it sounds a little complicated, but it's really rather simple. It says if f is continuous on a closed interval, then f has both a minimum value and a maximum value on that interval. And it's pretty easy to understand why. If you think about drawing a graph from f of A and f of B. Now here's A, here's B. So I have a little interval here. F of A, let's say, is here. F of B, let's say, up here. Now, if I'm going to draw a continuous graph, that just means that I am going to draw a line that is from this point to this point, and I can't lift my chalk from the board. You see, that's what continuous is all about. So I'm going to draw from here to here. Now, I can go straight from here to here, and the minimum would be here and the max here. But if I make it curvy, let's see how curvy I can make it here. You see, even if I make it curvy, I've got an absolute maximum and minimum involved in this graph. The absolute maximum is up here. Now the absolute minimum is this point or this point, maybe both of them. But this extreme value theorem just tells us the existence of absolute maximum and minimum and not uniqueness. That is, we might have a couple of points. That is, if this point goes down exactly to the level of this one, then we would have two values that have the same minimum for f of these 2 points, but they then are both absolute minimum points. Okay, so that's the idea. So it's rather simple. Now, when we apply the extreme value theorem to problems, all we have to do is keep in mind that the endpoints are to be considered as a part of the problem. For example, if we want to find the extrema of this function on the interval from -1 to 2, then we go about the matter in much the same way that we did before, identifying relative maximum and minimums, only this time we're going to involve the endpoints. Let's take a look at the graph this time. We'll know what's coming. We'll know the punchline here, but I think it's helpful if we can have a look at the graph just to see what's going on. Here's the graph, and notice that at the left end point we're at -1, 7. And the graph kind of flattens out right here, and then it goes to an absolute minimum at this point, which is 1, -1. And then we have an absolute maximum up here at 216. Now, -1, 7 is a relative maximum, but this is an absolute maximum. Let's see how we would find these points if we were proceeding through algebraically. We take the derivative function. The derivative is 12x cubed minus 12x squared. Now we want the zeros or undefined values associated with this function as our critical numbers. And so let's see, no values are undefined here, so we're looking for zeros. We factor over here this way. The value of x that causes this factor to become 0 is 0 itself. The value of x that causes this factor to be 0 is 1. So the critical numbers are 0 and 1. Now we're thinking about intervals. Now notice the intervals that I'm establishing here are from the left end point to 0, and then between these two, 0 to 1, and then from this value, this critical number, to the right end point. And we're thinking about the graph. We can kind of see it right here. I'm not going to belabor the idea of plugging in values and all of that kind of thing as we have before, because we have the luxury of the graph. But from -1 to 0, from -1 to 0, the graph is decreasing. All right, so we have a decreasing situation. Now, from 0 to 1, oh, the graph is decreasing in that interval as well. So we don't have a relative maximum or minimum at this point 0. And then we examine the next interval. Let's see, from 1 to 2. Well, from 1 to 2, in this interval, the graph is increasing. And so we do have a relative minimum at x equals 1. Now, in problems which are complicated and those which we are dealing with algebraically, we may not know at this point whether this value is an absolute minimum. We do from looking at the graph here, but we may not know at this point if we were just working algebraically. So here's what we would do to evaluate the situation. We're going to consider the endpoints, and we're going to consider this critical value. We don't have to consider this one because this is the spot where the graph kind of levels off. It's neither a relative maximum or minimum point. So we're just going to consider this one. So we go over to the side and we evaluate the function at the endpoints and at those critical numbers which give us a relative maximum or minimum. So it's f of -1, f of the left endpoint, you see. is found by doing this. Now in the f function we're just replacing x with -1, you see, and we're evaluating to find that value to be 7. And at that critical number x equals 1, replace x with 1 and evaluate, we find -1. And at the right endpoint, f of 2 is, let's see, replace x with 2, and we find the value to be 16. And now we're just looking at these values in order to identify absolute maximum or minimum points. So the biggest of these, 16, would be the position of the value for our maximum, and that maximum occurs at an x of 2. So the point 216 is our absolute max. And that's what we found before graphically. And the smallest of these is -1, and we know that that occurs at the point 1, -1. Now this idea of identifying an absolute maximum or minimum point can come into play in business and industry like this. Now, in an earlier section, we had a problem involving profit. We had a profit function involving hamburgers. I think this was a chain of hamburger stores or something like that. X is the number of units of hamburger units, if you will, produced, and P is the profit. And we're talking about an interval from 0 to 50,000. Now notice that we have a closed interval here, and we'd like to maximize profit. We'd like to know the production level that will maximize profit. Well, to do that, we calculate the marginal profit function. That's the P prime function, you see, from the P function, and we get this. Now, we go through the process in much the same way that we did before. We'd like zeros or undefined values associated with this. Well, there are no undefined values, but the zero can be identified by just writing this as 0 equals and solve. Multiplying through by 10,000, we get this. Adding x on both sides, we find x to be 24,400. Now, this is a critical value. We can tell by setting up intervals, if we want to, from the left endpoint to our critical number, we have a P prime which is positive, and that means the graph is increasing. The graph of P is increasing. And from our critical value to the right endpoint, P prime is negative, so P is decreasing. You see, well, gee, we have an increasing and then decreasing idea, increasing and then decreasing. Wow, we have a max in here, you see, at that juncture of 24,400. So we have a maximum. Now we could say it's a relative maximum at this point if we want to, because we need to evaluate endpoints, but it's pretty easy to see that because we have a quadratic function, the graph looks like this. It's a parabolic curve. And if it's increasing and then decreasing, we know that topmost point, that vertex, is the point we're looking for the absolute maximum. To evaluate the endpoints, though, we find P of 0, P of the left endpoint, to be -5,000. And P of our critical value is 24,768. And P of the right endpoint is also negative. So maximum profit occurs at a production level of 24,400, and we can tell what that maximum profit is going to be. It's 24,768. Now, let's make sure that I don't want there to be any mystery into how we made these calculations. P of 0, for example, is found by replacing x with 0 in our original profit function, and it's up here. So we would replace this x with 0 and that x with 0. These two terms go out and we have -5,000. And P of 24,400 is found by replacing those x's with 24,400 and then evaluating to find this, and so on.